Okay, so we're going to start. I want to show you gravitational potential energy from a different perspective. Then I want to connect it to our own gravitational potential energy. This is going to be a little on the technical side, but it's an important point. And so just be a little patient with it. Okay. So let me tell you what the proof is going to be. I want to prove that the gravitational potential energy from the force gm little m over r squared is, this is what I want to prove, that this is minus g big M little m over r. Okay. What does that not look like at all? We have gravitational potential energy. What's the old gravitational potential energy? mgh. So now, U equals minus G big M little m over R looks nothing like U equals mgh. I then want to show you how they're connected. Okay? So I also want to show how these two expressions are related. Part of why I want to show you this calculation is most of you are going to be taking Physics 126 in the fall. And one thing you're going to find out right away when you take 126 is that it's a lot harder than this course. Significantly harder. And you're going to see that week one. And part of it is that the math level gets kicked up a significant notch. And I want to kind of show you one of the notches you're going to get today. And so to actually show you how this is connected to that, I have to show you one of those little math things you're going to be seeing all the time next semester. Okay? So next semester, when you're taking that course, after about 3 or 4 days, you're going to realize it's a lot harder, and you're going to say, what the hell happened to the course? It's just the nature of the material. It's the material's more abstract, the math level gets kicked up a lot, and you just have to be patient with it. Okay? So that's what I want to do today. I want to show you why this is true, then show you how this is connected to that. Let's do that. Okay, so proof that U equals minus G big M little m over R. Okay, so let's say here's the Earth. Has a mass m. Here's some radius of the Earth, I'll call R sub b. And here's some little mass here, m. And I'm going to say the distance from the center to here is r. Okay. What would be the force acting on our little mass there? Gravitational force, good. So the force here, this is going to be the force of gravity here. What does that equal? Yeah, big G, M1, M2 in this case, big M, little m, over R squared. Okay, so that's the force. And what I'm going to do is I want to now find U due to gravity. Now we have to go back a little bit. Okay, what did we say is the formal definition of U? And remember, it's that really absolutely weird definition. What was the formal definition of U? I'll give you a hint. It involved, minus change in U, and this equals what? The work done by the conservative force. Remember, this is actually the formal definition of potential energy. It's absolutely bizarre, but this is what it is. Again, this guarantees, the reason you do this guarantees that this is actually path independent. That's why we do that. So what we're going to do, we're going to actually use this in this situation here, and then it's all going to fall out. We need one more thing. I have a class, my general relativity class is before this, and my mouth is entirely parched. Sorry about that. What do we know? We needed one more thing when we do these. We have to define something. We have to define, yes. Mm-hmm. Now the mass is just going to be given. We're just going to say the masses are M and big M. We need to define a zero of potential energy. So we need to define a zero of potential energy. And where we're going to take that, we're going to say it's at infinity. So we're going to say that if this particle is really at infinity, I can take the potential energy at infinity to be zero. Okay, so we define the zero of potential energy to be at infinity. So what we're going to do, we're going to calculate the work done by gravity, taking this object here and moving out to infinity, and then everything's going to fall out. Okay? So we're going to say the work done by gravity is going to be this minus change in U of gravity. And this is always the final minus initial, so this is going to be minus U at infinity, because we're taking this object out to infinity. This is our final, this is our U final, minus our U initial, and our U initial is U at R. Does that make sense? Questions? Go ahead. Fair enough. Okay. Again, this is actually the definition. Again, the reason why we do it is that if you have this definition, it doesn't matter how you get from here to there, you'll always have the same answer. So that guarantees that this is actually independent of the path. So now we just have to work out the work done by gravity. Okay, so you tell me how to calculate the work done by gravity. So I'm going to take this object and move it off to infinity here, which turns out infinity is right here. Incredible. Okay, and we want the work done by gravity. So you tell me how to find that. You can do force times distance only when the force is constant, but let's go off with that. Modify that so it's going to be okay here. So what do we do here? So we're going to move this object out here like that. This is infinity. So what am I going to do? I'm going to take this object here and I'm going to move it a tiny little distance. What will I call that tiny little distance I'm moving at? What do you do for a tiny thing in calculus? You always put a D in front of something that's small. We're going this way, so this is going to be our tiny little distance. I'm going to call that dr. Okay? So I'm going to assume that I'm going to move this object some tiny little distance dr, and what will I assume about that force? This is such a small distance that it's going to be constant. So I can consider the tiny work to move the object from here to there is going to be the force of gravity times dr. Now, is that positive work or negative work from that picture? I'm pulling it this way, but what's gravity doing? It's pulling that way, so it's doing negative work. So this is going to be negative work here. So this tells me that this dW is minus big G, big M, little m, over r squared dr. So if I want the total work done by gravity, what do we have to do? All right, that gives me the object here. Now I have to move it here, then I have to move it here, then I have to move it here, then I have to move it here. You have to integrate. And integrate from where to where? From here, little r to infinity and beyond. Okay, so we get this guy. Now, in calculus, sometimes you learn things and you think, there's no way I'm going to use half the stuff I'm learning. It turns out, Calc 1, 2, and 3, you pretty much use every single thing that you learn in those courses. At some point, it's going to come along. Where do you see this? This is our friend D. What do mathematicians call this? Yeah, this is an improper integral. Now, again, I mentioned this point before. I don't care how the math department thinks about my math. I do care how my wife thinks about my math. So we're not going to share with my wife how I'm going to have you do this. How should you formally do this? You don't have infinity here. What do? You make this some constant. Okay, so usually they call it b, but you could call it, I'm not going to call it m because of the variables here. But then you take the limit as, yeah, that upper limit goes to infinity. That's how you formally do one of these things here. I'm not going to do that. I'm just going to put in the slash and the r and the infinity here and evaluate it. It's going to be fine. This right here, okay, so your tiny work is your force times your distance, okay? But what is the force of gravity? The force of gravity is this guy here. Okay, so that's your tiny work here. So then the total work is integrating all these little contributions. No, where would be 0 here? That'd be right here. The r goes from the center of the Earth or to whatever planet you're on out to this question here. Okay, so we're here, okay? Then you're going out to like that. I've integrated this guy here. So this guy here, I said this guy is going to be the integral of the dW's, like this. I'm just calling this guy here W gravity. Okay. That makes sense? Okay. So let's do that. So, what can you pull out of the integral? Yeah, the whole numerator comes out. Get this here. What's this guy? No. If you had that, then you have an ln. We have that. It might be easier if you think of this as being r to the minus 2 dr. Yeah, this ends up becoming minus 1 over r, evaluated from r to infinity. If you didn't know, you could check this. This is really minus r to the minus 1 power. The derivative of r to the minus 1 power is this guy right here, so it checks. Okay, these minus signs cancel. And then we're going to do what the mathematicians tell us not to do. We're just going to put in the upper limit and the lower limit and call it good. So you're going to have 1 over infinity minus 1 over r. And again, my wife would be very upset if she saw me do that. I showed her what I did once, and her response was, "You're part of the problem." Sorry, okay. Okay, 1 over infinity is, try again, 0. 1 over big is small. So the work done by gravity is minus big G big M little m over r, and we know that this equals minus delta U. The minus signs go away. This is what? This is going to be U at infinity minus U at r. U at infinity is by definition 0. So then I can solve for this guy here. So U gravity is minus big G, big M, little m over r. .999% of your life you'll never use that expression. Okay, when will be the only time you use this? Basically, when you're getting r's much larger than the radius of the Earth. So in other words, let's say you're doing a rocket. If you're launching a rocket into space, if you're using a rocket into space, the r gets quite large. You'd have to use this expression. You can't use MGH anymore. That expression MGH only works near the surface of the Earth. So if you're doing anything with a rocket, you have to do this. If you're doing anything planetary, let's say you want to study the moon, then you'd have to use this. Okay? Yeah, because what's going to happen here is, so if you draw a little picture of this. Okay, so here's the Earth. Okay, so let's say here's something here. Normally this distance right here, I'll put it up here. This is what we call H. I'll make this a little bit bigger so the people on Zoom can see. This is H. H is always your distance from the surface here. Normally, what is this H? This H is usually much smaller than the radius of the Earth. This I've drawn to a stupid scale. This H is not smaller than this. This is comparable. So you can do this here. Normally what you do, your H's are really, really close here. You're almost on top of that surface there, on top of that line. So your H's are really, really tiny. So what's going to happen here is your force of gravity is almost a constant. That's why you can do that. When you're getting up into here, your force of gravity goes as 1 over the distance squared, right? 1 over the distance squared here. That's not variable. If you're really, really close here, like this R barely changes. This goes from the center of the Earth out to the object in question. And that's what you can do with that. Does that make sense? Think you had a question, James? Okay. Yeah, so these cancel, making everything positive. Then this is this. That's your baby. Yep. When you're working with for NASA, okay, then you have to do something like that, or rockets. So if you're not doing rockets, if you're doing speedboats and stuff like that, you'll almost never use it. It's not wrong, but it's a lot harder. Yes? Cars are on the surface of the Earth. Unless that car takes off, you're good to go. Just MGH. As long as you're on that surface of the Earth, you're not, if you're launching those into space, then you get this. But it turns out those cars don't launch into space that often. Okay? You know if they do? What? Yes, well, probably, because I think they went up fairly high, didn't they, in that? Okay, so let me show you a case where you could use this. So let's see if we can do this. Let's ask how fast must an object travel to escape the Earth? So basically, I want a big slingshot. I want to make something go really, really fast, and I want that slingshot, whenever I'm throwing, to leave orbit and go off into space. How fast does it have to be going? So here's our little object here. This is the Earth. This is going to have some velocity, and call this v escape. Okay. So this is on the surface of the Earth. This is m. And I want that thing to travel and escape. So first of all, we have to understand what this means here. If this object actually escapes the Earth, where is it going to end up at? So I have a big slingshot. I go like this. I throw my rock into space. If that escapes the Earth, where do I really want it to go? Infinity. Okay, so what we're going to do this, I'm going to say this is going to go so far away, I can effectively call this point here infinity. If you just reach infinity, because again, we just want the minimum velocity to get there. If we just reach infinity, what's our velocity? If we just escape. Right? We go, we slow up, we slow up, we slow up, because gravity is always pulling us that way. When we reach infinity, which we never do, what do we want the velocity to be? 0. So if you just escape, the velocity at infinity is 0. Okay, this looks funny, but what kind of problem is it? Keep going. It is a work energy problem. It's a conservation of energy problem. Again, here's your before picture. Here's your after picture. Before and after pictures are almost always going to be a conservation law of some form. So we're going to say this energy here equals that energy here. So you're going to say E initial equals E final. What is energy always made up of? Kinetic and potential. Okay, what's my final kinetic energy? Out here. 0, because what did we say the velocity is at infinity? 0, because you just get there. What is the potential energy at infinity? No. What do we say U is at infinity by definition? 0. And you can see that if your R is really, really large, what's 1 over large? Small. So you can see this is going to go to 0. So at infinity, this is 0. Okay. What's your kinetic energy always? So here on the surface of the Earth, what's kinetic energy have to be? No, it's not starting at rest, because we're going to launch it into space. That has to be your 1/2 mv squared. So this is going to be 1/2 m. I need more room. This is your 1/2 m v escape squared. Plus, okay, and this is your 0, 0. Okay, what is the gravitational potential energy at this spot here? Don't do MGH. If you did MGH, again, when is MGH valid? Yeah, you have to be near the surface of the Earth, okay? Okay, so let me finish up the note. I didn't quite hear what you had said. So you can't do the MGH here, because eventually this thing is going to go off to here, which is not the surface of the Earth, okay? So we have to be a little more careful. What did you say, Kylie? Yeah, it's going to be our friend here. For right here, this is going to be our minus g mass of the Earth, okay? Mass of that object over little r. This object is starting right here. This is little r. What is little r? R is nothing but the radius of the Earth. So this is going to be over the radius of the Earth here. So now if we solve this, yeah, we're not putting, if you put an air resistance, then you'd have to be going faster because you're going to lose a lot of energy from that. So I mean, if you're doing like a rocket and stuff like that, and also when you start doing other things too, you have to worry about minimizing things, and so sometimes you have these really bizarre paths, and you take this bizarre path to minimize certain things, and so you can, you have to start doing clever stuff. Yes. Yeah, you'd have to, the force of gravity is always there unless you're kind of infinitely far away, and you never really can be, so there's always a little bit no matter what. So you're going to take this over here. What nice thing happens? Yes. Yes. No, how come? You could so if you want to do it that way, what you would have to do, okay, so this question is, suppose you wanted to put an air resistance. And so if you wanted to put an air resistance, you couldn't start here. What you would have to do, you'd have to, you start this right here, you then have to put in the, the work you do air resistance, okay? What's tricky about that? It's not constant, okay? So what you'd have to do, you'd have to minus the force of air resistance, okay, times dx. Then you have to integrate this from the radius of the Earth up to the radius of the atmosphere, or wherever the air basically goes to zero, wherever the air goes to zero. This right here would be your b times v. You can see this is a function of x, or I should say r here. So you'd actually have to do something a little tricky here. And so you have to actually do something different. What? I'm still can't. Oh, it cancels out. Okay, yes. Okay. With your mask on, and then also, as you can already hear here, there's really a bizarre echo in this room. I hate this room completely. I'm hoping in the fall all these damn masks are off and I can see what you people look like, and we can actually talk. Not that you'll have me next semester, but at some point you will, hopefully. And then we won't be in here. We'll be in some room where we don't have a stupid echo. Okay, so the little m's cancel. I want to solve for this via escape. So I take the 2 over here. Okay, take the square root, and this is my escape velocity. If you work it out, it's something, it's actually quite large. It's several kilometers per second. It's actually quite high. Where did what? No, there's no time in here because what we're doing it from a conservation of energy point of view, so it completely bypasses any of that, which is why the calculation is easy to do. Now this means something here. Why do we have an atmosphere? You can go to some planets and you have no atmosphere. How come? When they were formed, they probably had an atmosphere. Well, you can have some stuff. What can happen here, depending on the mass of your planet and the radius of your planet, this escape velocity can be quite low. So what can happen, the planet can heat up enough that actually any atmosphere it has will actually bleed off into space. It turns out that can't really happen to us with the exception of one thing. In principle, there's only one really, truly non-renewable resource we have. Does anyone know what it is? It's not one bit obvious. Helium. Where does helium come from? Well, where does it come from, though? True, but I mean, you get helium from there, but the helium on Earth, where does it come from? It's not obvious. It comes from the ground. Where in the ground? Radioactive decay. So if you look at alpha, what is alpha decay? Right, so let's say you have a big nucleus here. Let's say here's some nucleus here. It decays, and so, you know, something goes out this way, then you get this alpha particle going out this way. What is an alpha particle? It's a helium nucleus. The helium nucleus goes, it eventually acquires some electrons and becomes a helium atom. So you actually, all the helium that we have comes from radioactive decay. And there's only so much radiation we have, so eventually that'll be gone. Now, you could say, well, the atmosphere is constantly being, basically, if you have this helium being pumped into the atmosphere, why don't we all sound like Donald Duck? Or some chipmunks or some irritating cartoon character, you know, you're having those really irritating voices. Why don't we all sound like Donald Duck or Chip and Dale or Alvin and the Chipmunks? Okay, I can't think of almost anything more irritating than Alvin and the Chipmunks. If I were a spy and if I were captured and they wanted information, if they just played Alvin and the Chipmunks, I would tell them anything they wanted to know. Just make that stop. Oh, please make it stop, okay? But anyways, why don't we sound like Alvin and the Chipmunks? No, it's because of this. Okay, it turns out that, you know, the gas is heated up in the atmosphere. If you look at that distribution of velocities of the gas particles, there's a tail. So if you look at the number of molecules here versus the velocity here, you get this distribution you saw in chemistry, that Maxwell-Boltzmann distribution. There is actually a tail of it here, which actually has a velocity greater than this. And with helium, this is not a minor point. All the helium that we have will eventually bleed off into space and never come back. So in some sense, helium is the only non-renewable resource we have. Kind of interesting. That's why we don't sound like Donald Duck, because basically part of it is always going off into the atmosphere. Okay? Pretty cool. Okay, how are we doing on time? Great. Now, I want to ask, how is U equals minus G big M little m over R related to U equals MGH? Okay. Before I answer that, I need one thing. So before we answer this, let's ask the following question. Why is G equal to 9.8 meters per second squared? It's not that just somebody clapped their hands one day and said, oh, I think G, and I think it's 9.8 meters per second squared. It turns out it has to be that value. What? No deciding here. Let's actually figure out what G has to be. So here's the Earth. And here we are. This is us. Turns out we have a mass m. If I had to say, draw the free body diagram for that, what's the free body diagram for this? Okay. You have the normal. We have the weight. What does weight equal in why do we have weight? What causes our weight? Yeah, the Earth is actually putting a gravitational force on us, pulling us toward the center. This weight that we have, this is a force here of gravity that the Earth puts on us. That's what gravity fundamentally is. Okay, let's put some things in here. What is this? This is going to be G, mass of the Earth, our mass, over, what is the R squared here? All right, this is the R here. That little r is nothing but radius of the Earth. So this is radius of the Earth squared. Hey, let's look at this crazy thing here. G, mass of the Earth over the radius of the Earth squared, this is a constant. Hey, what might be a nice name for that constant? Little g. We can't put a value in it because there's nothing zero here. This would be little g. So this is why the weight is equal to mg. Remember before I told you that the weight was mg and we do a proof later on? This is the proof. So if you were actually on Jupiter, what would be the g for Jupiter? What would you do? You'd have the mass of Jupiter over radius squared of Jupiter. So any planet you're on, you can do this little calculation. You can calculate your g, and you can figure out how much you would weigh on any type of body like that. Yes? Sure. Okay. That's what you do with any of those things. Does that make sense? Okay. Now, let's figure out how these two are connected here, but keep this in mind here. I'll write this off to the side. So you have that this g is, okay. Okay, ready for this proof? Be patient with it. It's going to be a little on the hard side. Okay, it's not hard. It's actually very straightforward, but just so you know, the first time you see this, it's going to be straight from hell. The reason I'm doing it is, first of all, because you should see it. The other thing is, I want to get you ready for 126 next semester. So when you see this again in 126, it still won't make any sense. You have to see this about 3 or 4 times before it starts making sense. I'm not going to hold you responsible for this because it's not one bit of an obvious derivation. Okay. So here's the Earth. Here's our little m here like this. This distance here, that's h. This h here is the distance above the surface of the Earth. And this right here is the radius of the Earth. Right? So we have some little mass here, m. There's some distance h above the surface of the Earth. Okay? Let's calculate u for this. So u for this object right here is this. Okay? What is r in this case? Where's r in this? Where's little r in this picture? Yeah, this right here is r. From here to there, this is r. So this r here is radius of the Earth plus h. So let's put this in here. Okay, I'm gonna factor out the radius of the Earth here. You tell me what I'm left with. If I pull out an r in the bottom, what am I left with? No. Remember, this, when I distribute this through, I better get this right here. Yeah, this has to be 1 plus h over re, right? This times this is this. This times this is that. So I'm going to rewrite this as the following. And this guy here is small. Well, oh, okay. So I wrote this here. I have no idea why. Call me on it. Don't let me write something moronic. Thank you. Okay. So we really have 1 plus something small. I'm going to call this x. So let's ask what is 1 over 1 plus x? Okay, you're on Calc 2. You know what that is. What is that an example of? Now, one of the most important things you learn in Calc 2. The integration techniques are indispensable in Calc 2. What's the other big thing you learn in Calc 2? Something else? Taylor expansions. Taylor expansions are the absolute workhorse in life. If you have no clue what to do when you're dealing with a problem, just say, I think we should do a Taylor expansion. Even if you're wrong, people will think you're smart. Like, you know, but you have to do it authoritatively. See, you want your glasses on, like this, and you want to go and pull them off authoritatively. Like, I think we should do a Taylor expansion. People go, wow, how did you think that? Look how far I got. You know, Taylor expansions are great. Yes. Yes. So if they're down, you put the tip in here like that. That's very important. Then what you can then do is usually then just say random Star Trek stuff too. You know, talk about triphasic shielding, metaphasic shielding, trioscillating phase arrays. It'll be great. So what you can do is you can do a Taylor expansion here. What is this Taylor expansion called for this one? This is the binomial expansion. So you're going to use the binomial expansion. I want to show you how you can do that without actually kind of in an easy way. So let's say you're back in high school. So let's do this from high school. So use high school knowledge to do this. So if you had 1 over 1 plus x, what would you do in high school? In high school, you'd do the following. You'd say, this is the same thing as 1 plus x, and you divide 1 into this. Okay, how do you do that in high school? 1 goes into here, 1 times. 1 times 1 is 1, plus 1 times x is x. You subtract these two, and this gives minus x. How many times does 1 go into minus x? Minus x times. So minus x times 1 is minus x. Minus x times x is minus x squared. And take the difference again. This is now x squared. Okay? And you keep on repeating this. And so what you end up with is you end up with the following. Is you get that this is this. You get that. Now x is small. If you have something very, very small and square it, what happens if you square something small? It gets smaller. If x is small, x squared is smaller. And likewise for all the other ones. So what I can really say is that this 1 over 1 plus x is to a very good approximation 1 minus x. So let's put that in for here. In our case, we have this x as h over r. So in our case, we have this x as h over r sub b. So we have this. So this is 1 minus h over r sub b. You're going to take this and put it into our friend over here. Okay, so this whole mess here gets replaced by this guy. That gets over here. So this is now 1 minus h over re. Let's multiply that out and we get something cool. This times this gives me g m little m re squared h. This is a constant. Constant doesn't matter, but this is a friend. What do you know about this right here? That's our friend little g. So I get this is that this u equals a constant, which we can neglect, plus mgh. That's the connection there. Okay, that's the sophisticated. Okay, the first time you see that, I remember as a student seeing that. I had no clue what happened. Okay, the first couple of times you see that argument, that's really subtle, and it's not obvious what happened. Next semester, you're going to see that argument all the time. Constant, a constant. Constant. Okay, so this is our MGH here. That's the connection. Okay. There's a slightly easier way to see this with a picture. Okay. If I had to graph this, if I had to graph this versus h, what would that look like? A straight line. Okay. If I had to graph this, let's say here's you. This is what this graph looks like. Let's say here's the radius of the Earth. Like that, okay? So this right here is an h. This value here is in radius of the Earth plus h. What can you say about that little tiny piece here? What does that look like? Looks exactly like that straight line here. Okay, so all you're doing here is you're concentrating on a tiny little section of that graph there, and that's a straight line there. Very subtle. Okay, what I did today was a remarkably subtle and not the most obvious argument here. Okay, I'm not going to hold you responsible for that, but I do want you to actually know where it comes from because it's important, and you're going to see this all the time next semester. Have a fantastic weekend.